Our next speaker, ladies and gentlemen, is going to speak about scientific cooling for injection molding. Mr. Mark Brown is a mechanical engineer by training, president and CEO of Berger and Brown Engineering. Based in Grandview, Missouri, Berger and Brown manufactures engineered products related to mold cooling and in-mold sensing and holds 10 patents and 14 trade names for its products. Scientific Cooling, Brown's brainchild, was successfully launched in October 2013 by Phil Berger, founder of Berger and Brown Engineering. Berger spent 18 months in the lab collecting data and developing the inaugural materials with Brown support and collaboration. Today, Scientific Cooling continues to evolve as more time in the lab adds materials and class participants add perspective. Please get your hands together, ladies and gentlemen, for Mr. Mark Brown.
Thank you. Good morning. TAGMA, thank you for inviting me here and giving me this opportunity. And thanks for your patience and everybody being here. Slides. Oh, that's the one. So, see if I can get back to the beginning here. There we go. I'm CEO of Berger & Brown Engineering. I'm Mark Brown. And basically, we are the makers of smart flow products. We optimize mold cooling through turbulent flow and use sustainable practices to conserve energy and water. So how do you measure what's optimum for mold cooling? How many people know about Reynolds Number? Show of hands? Just a few here in the front? Well, we've got a few in the back as well. So basically, what this graph is showing you is down here in low flow conditions on the left side, small changes in flow have a very adverse effect on steel temperature. So once you get past a Reynolds number of 4,000, small changes in flow have very little effect on steel temperature. Once we get to the above 8,000, basically we're at a place where it's wasted capacity. So what we teach is that down here in low flow conditions or laminar flow, this is unstable steel temperature. In the sweet spot between 4,000 and 8,000, we're stable and efficient. Anything above 8,000 is wasted pumping capacity. So what that means is that turbulence equals process stability and optimum cooling. So how do we figure out where we need to be in our cooling flow rates? We have an online calculator called the Turbulent Flow Calculator, or Turbulent Flow Rate Calculator, and down here is the website, but I'm going to pass on that and just show you what happens. So if you kick at the metric and you put in 40 degrees C, an 11 millimeter diameter cooling circuit, for a Reynolds number of 4,000, we need to be at 1.42 liter per minute. So let's change that and get it to the middle of the process window, and let's say 6,000 on the Reynolds number. Everything else stays the same, so we need 2.13 liter per minute to maintain 6,000 on a Reynolds number. So what happens if we go colder on the water? Some people like to run at 20 degrees C. What happens? Our flow rate has to go up to maintain 6,000 on a Reynolds number. The reason is the kinematic viscosity is dependent on temperature. And as the temperature gets colder, the viscosity changes in the water. Hence, our flow rate has to go up. If we're going to run at 20 degrees C, most likely you're going to have to run glycol. So we put in 30% glycol, and all of a sudden, our flow rate has to go to 6.74 liter per minute. Glycol is bad for mold cooling. So we recommend that you don't do that. You can run at 40 degrees, be a lot more efficient, a lot more sustainable with your energy and your water, and stay at the 2.13 liter per minute range. So the things that depend, or that Reynolds number depends on, is flow rate, port size, water chemistry, and water temperature. Yesterday, Volkswagen, for those of you that were here, made the comment that India has no mold cooling involved, that you guys know nothing about mold cooling. So that's what I'm here trying to show you guys. So this here, okay, now that we know, okay, we need to be at 6,000 and we know how to get to 6,000, what's it do for us? So basically, where is the water going to flow in a mold? Let's say you have 4 circuits that are straight through, you have 2 circuits that are tortuous in path, and you have 2 circuits that are baffled. Where's the water going to go? Path of least resistance. It's going to go through the easy flow rate. So that's what this represents. This is an animation you can go online and look at as well. The top circuit is a straight through circuit. The bottom circuit is bubblers. And the middle circuit is a tortuous path. And as you can see, we've got 15,000, 4,000, and 1,000 on the different circuits as far as our Reynolds number. That's a problem. All the water is going through the first circuit. But how do we know that? So the manifolds create order from chaos. So we put flow meters on there. Now all of a sudden, okay, our flow meters tell us exactly what's going on in the mold, and we put them on the return side. If we have turbulence on the return side, we know we have it on the supply. So the first circuit, again, we have a large flow rate. The bottom circuit, we have no flow almost. And the middle circuit, we have a little bit of flow. So we have 15, 4,000, and 1,000. So really, all the water on the top of this tool, the top of the parting line, is really cool or cold. The bottom of the parting line, we're probably seeing hot spots. So how do we fix that? We put regulators on it. So the first circuit, we've dialed back on a regulator. We dialed it back to 6,000. That's our sweet spot. We know that. Now we've got 9,000 and 3,000 on the next 2 circuits. So we adjust the second circuit to 6,000. The bottom circuit now has 7,000 on our Reynolds number. So we can adjust it down to 6,000 as well. Now we have a balanced tool, and we're optimizing, again, the energy and the water cooling, or the water itself. So from that, basically, these are all the various types of mechanical flow meters that we have to offer. You can get pressure, you can get temperature with these flow meters, and they're all the way up to 2 inches, 2 inches BSPT, or I'm not sure what you guys use here, but we offer the metric version as well. This is our electronic flow meter, and basically this is a flow and temperature monitoring, very accurate, plus or minus 1.5% of scale, and we can go from 3/8 all the way up to 1.5 inches. Basically, you can land these on a PLC or a data acquisition system like an eDart, if anybody knows what an eDart is. With this, you can also land those devices, up to 8 of them, on a Bluetooth device. And that Bluetooth device, you can then take your smartphone and you can see flow and temperature on a smart device or a tablet. You can also download the information for flow and temperature with timestamp dates and basically certify that molding process. There are more and more customers, especially in the automotive industry, which is a big sector here in India, that are wanting all this data to prove that you guys are making your parts according to their recipe. So this is a very inexpensive way of certifying those processes. The next step up from that is you can actually land an Ethernet on the Bluetooth device, and as a result, you can use a PC to set high and low limits on flow and temperature. And if you go up to 8 circuits, and if you go out of that process, basically you'll get an alarm output that's a dry contact that you can land on your machine to shut it down or turn a light on, whatever you need. And then basically you are at that point notified that you have a problem with that particular Bluetooth device, and you can go to the computer and determine which device it is and fix it. The next step up is user interfaces. So these are all programmable: flow, temperature, high and low limits, turbulent flow indication, Reynolds number. You can also visually see Reynolds number on this particular unit. You can have a remote and or local display. This is the regulator side of the equation. So these are various regulators. We have Delta Q, which is modular in its approach, and you can put all of our devices on top of Delta Q to again regulate flow. And then you have the machine bodies. We can go all the way up to 1 inch NPT or BSP to handle your needs. We offer a educational component. We started back in 2012 specifically for cooling. Scientific cooling is a 2-day intensive course. It teaches you the physics behind mold cooling, thermal coefficients of heat transfer, all about turbulent flow, heat capacities on resins, and so on. So this will give you a very intensive 2-day course. A lot of calculations. You do have to pass the final with a 70% to be certified. It's not a, you come and you get a certificate just for participating. You have to pass the final. How many people have tools with scale built up in the water cooling? Raise a show of hands. Is anybody? Nobody has scale in their tools. Okay, thank you. This is very important. How many people drive their cars and don't change their oil? Anybody? Basically, what this is, if you put scale in a cooling circuit, it's a great insulator. So you can see down here at the bottom, thermal coefficients, beryllium copper is 38. P20 tool steel, 16.8. Calcium scale, 0.05 to 0.5. It's awful. So 2 millimeters of scale represent the same thickness as, or thermal coefficient of 2 inches of steel. So this is very important, especially now that yesterday in the panel on 3D printing, they were talking about conformal cooling and being able to print the cooling circuits up close to the cores and cavities of the surface of the steel. What happens, again, that's a great thing, but if you don't take care of the tools and maintain them, what you've done is basically put 2 inches of steel, again, between the water and the surface of the cavity. So it's very, very important to pay attention to this. So I'm gonna go on real quick here to another initiative that's called SMED. How many people know about SMED? There's a few out there, yep. Single minute exchange of die. So if a tool's not making parts, that molding machine's not making money. So you have to change those tools very, very quickly. We have a few products that support that effort. This is the fast tie. It ties the ejector plate on the molding machine to the ejector plate on the plate or on the mold itself, and it does it very quickly. It's a mechanical hookup with a pneumatic release. This is something that I encourage you to explore. This is a swap valve. Basically, you can purge your mold very, very quickly with compressed air with the movement of a handle. And the Taco air separator keeps the water in the cooling circuit and pulls the air out, or allows the air to leave. And this is a typical setup that you'll see. And last but not least, I'd like, Stiak is our exclusive distributor here in India. If you guys could stand up, there's a few of you in the room, I believe. Oh, come on, guys, where are you at? There's Anil. There's a couple back there. I see them raising their hands. There they are. And is Corey here? Yeah, stand up, Corey. So if after this presentation you guys have questions, seek these guys out, including myself, and we'll be happy to answer any questions for you. Thanks for your patience, and again, Tagma, thank you for the opportunity to be here. Appreciate it. Thank you.
Thank you. Thank you very much, Mark. And may I request Mr. Vivek Naniwadekar, Executive Director, Fibro India, to please step up to hand over a memento to Mark Brown. Ladies and gentlemen, President and CEO of Berger and Brown Engineering, Mr. Mark Brown.